Hi, and welcome to this A-level physics lesson on the conservation of momentum. Now, this would also be applicable for an A-level maths student looking at mechanics, but primarily this is going to be focused on the A-level physics course and what you need to know for conservation of momentum. Now, momentum, we should hopefully remember, momentum is calculated by multiplying mass and velocity. So the equation for momentum is equal to mass times velocity. And momentum is a vector quantity. Hopefully you're super familiar with that, but as a reminder, a vector quantity has both a size and a direction. So directions are really, really important when we are thinking about momentum, especially if I'm considering more than one object in a system. Now, the principle of the conservation of momentum says that momentum is maintained in a closed system. So the momentum before an incident in the system is going to be equal to the momentum afterwards. Now, momentum questions tend to focus on things like collisions, so two things coming together, or they focus on something breaking up into two things. And in both scenarios, we would consider the momentum before the incident, whether that's two things coming together or two things breaking apart, and the momentum after the incident. And by the principle of the conservation of momentum, those two numbers must be the same. Let's have a look at an example question where hopefully you'll understand a little bit better exactly what I am talking about. And in this question, we are going to have a look at something breaking apart. So in this question, we have a spacecraft called Deep Space One of mass 486 kilograms. And the statement says the ion propulsion system on Deep Space One expels 0.13 kilograms of xenon propellant every day. The xenon ions are expelled from the spacecraft at a speed of 30 kilometers per second. The speed of the spacecraft is predicted to initially increase by about 8 meters per second each day. Use a calculation to comment on the prediction made. So this is an example of something breaking apart. And the first thing we're going to do, as with any mechanics style question, is we're going to draw a diagram. So in the before scenario, we've got our total spacecraft. And what that is doing is just existing, right? It's just, we can assume it's motionless or stationary. In our relative frame. In the after scenario, we have our spacecraft, but in this scenario, it is expelling 0.13 kilograms of xenon propellant at a speed of 30 kilometers per second. Now, the speed of the spacecraft is given in meters per second. So what I'm going to do is turn that kilometers per second into meters per second by timesing it by 1,000. So the xenon is moving at 30,000 meters per second. And we need to work out if this statement is correct, that the speed of the spacecraft increases by about 8 meters per second each day. So what we can do is assume that in our relative frame, the total momentum before the whole thing kicks off is 0. Okay, in our relative frame, the total momentum before the xenon is expelled is 0. The total momentum after is going to be the momentum of the xenon minus the momentum of the spacecraft. And we know that has to be equal to 0 because the total momentum before was 0. So what we can do is work out the momentum of the xenon. We're going to do mass times velocity, which is 0.13 times 30,000, which should give us 3,900 kilogram meters per second. 3,900 kilogram meters per second. This should be the momentum of the spacecraft. So using the principle of the conservation of momentum, we can say that 486 times the velocity of the spacecraft is going to be equal to 3,900, which means the velocity of the spacecraft is going to be 8.02 meters per second, to three significant figures, which is roughly 8. And so using the principle of the conservation of momentum, we have shown that the statement is accurate and the speed of the spacecraft will initially increase by about 8 meters per second each day. And there you have it, nice 4 marks. If you're curious about where the marks came from, the first mark came from working out the momentum of the gas, the xenon. The second mark came from working out the momentum of the, equating that momentum to that of the engine. The third mark came from working out the velocity, and the fourth mark would come from saying that therefore the statement is accurate because it's a roughly 8 meters per second. And that is where our 4 marks came from. So there you have it, a quick roundup of the principle of the conservation of momentum. Now there is a worksheet that accompanies this video, which includes some past exam questions, some more wordy, some more calculation based, looking at the conservation of momentum. But just remember, the momentum before an incident, whether that be a collision or a breakup, is exactly the same as the momentum after. I hope you found that useful. Any questions or comments, pop them in the box below. But otherwise, thank you guys for watching, and I'll see you next time.